In the last video, we took a look at the definition that you see here at the top of the screen. Now, this definition allowed us to be able to compute what we are going to be calling a surface integral. But it required something very important. It required that the surface sigma that we were working with could be parameterized. And so that's going to be an important thing that we'll see down here in example number 1. Let's take a look at our first surface integral. I want to compute the surface integral of x squared ds over sigma, where, and again, I apologize, I have another typo here, where sigma is the unit sphere. So that's the surface that I'm working with, a unit sphere. And you could probably tell right away that this guy here is a sphere and it's got radius 1. So it's a sphere with radius 1. Now, again, it's going to be really difficult to try to compute this surface integral unless I can do the following. I first need to understand how I would parameterize this particular sphere. I'm going to need to convert this x squared into something with my new parameterization. And once I have that parameterization, I'll be able to put this dA, that is in terms of u's and v's, and then hopefully determine my bounds. So let's start with finding the parameterization. So I'll start by saying this. We need a parameterization for sigma. Now actually this is really simple to do, and if I take a look at the hint, you'll see exactly how. I want to use what I know about spherical coordinates to find parametric equations for sigma. Well, if sigma here is a sphere, then I could say something like the following. So what I know by parametric, or by spherical coordinates, is that my value of x, remember, is given by rho sine phi cosine theta. It's also the case that y is given by rho sine phi sine theta. And you might recall that z is just given by rho cosine phi. And of course there were some restrictions here on what these angles were going to be. Remember that, let me move this around a little bit. Remember that the angle of theta was going to have to exist from 0 to 2 pi, but the angle of phi was going to have to exist from just 0 to pi. So I have these restrictions here, and what I'd like to do with these is to think about how can I turn this into a parameterization. Well, it's actually going to be really simple, because what I'll notice here again is that if the r for my sphere is 1, that's the radius, then that of course means that rho is a value of 1. And so what I can actually do is state this. So r, which I'll say is going to represent my parameterization of the surface, is going to have two variables. I'm going to call those variables theta and phi. You can imagine them as kind of taking the traditional roles of u and v. And you'll notice that I know exactly what to put in place of x, because I already have a formula for this. If rho is a value of 1, I can simply go ahead and replace with these values. Similarly for y, and finally for z. So I have a parameterization automatically, and again, I already know the bounds on my parameters of theta and my theta and phi. I already have bounds on those. So this is great. I have a parameterization. So this here is a parameterization of sigma. All right, so according to what we have then in the definition up above, I need to think about how I transform this integral into things that use u's and v's, or in this case, thetas and phi's. Well, notice that replacing x squared is going to be very, very simple, because I already know what x is. It's this sine phi cosine theta, and to square that isn't difficult at all. The other thing I'm going to need, though, is to find the magnitude of the cross product of the partial with respect to u and the partial with respect to v, or in this case, partial with respect to theta and partial with respect to phi. So let's go ahead and see if I can do that. All right, so I'm going to go ahead and down here I'm going to set up my r theta cross r phi. Okay, so if I go ahead and I compute this, let's see what we have. So I'll write my derivative with respect to theta first, and let's see what we come up with. In this case, I'm going to end up with, if I do my partials with respect to theta, let's take a look carefully here. So I'm going to have to take the derivative of that cosine, and I'm going to end up with a negative sine phi sine theta. I'm going to end up with a sine phi cosine theta, and then I'll end up with a 0. If I was to re-go through and do my partials with respect to phi, I'm going to end up with cosine phi, cosine phi cosine theta. I'm going to end up with cosine phi sine theta, and then I'll end up with negative sine phi. Of course, then I'll have my I, my j, and my k, and my cross products ready to be calculated. Now I'm going to write the result down here, and let's see what we're going to get when I do my cross product. I'm just going to put this right into this kind of vector notation. So let's see. If I cover up these two rows here, I'm going to get sine phi times a negative sine phi. So I'll end up with a negative sine squared phi cosine theta. And of course, that's minus 0 coming across. I'll then remember over here, I'm going to have a negative. And let's see, I'm going to get a positive sine squared phi sine theta, ultimately minus what I'm going to get when I do this times 0, which is of course just 0. So I'll go ahead, and just close that set of parentheses off. I'm just going to have a negative multiplied to all that. The final piece here is going to be the more complicated piece. Let's see, I'm going to get a negative sine phi cosine phi, negative sine phi cosine phi, and then a sine squared theta. I'm also going to get a subtraction, and hopefully I can squeeze this in here. Notice I'm going to get, again, a sine phi cosine phi, and now a cosine squared of theta. So if I was to simplify this down, there's not much that I can do with this first component over here. The second component I can make look a little prettier by at least not putting that extra set of parentheses in there. But you'll notice that at the end here, there is some stuff that's in common. I have this negative sine phi cosine phi that's in common between both terms. And when I factor that out, I'm going to be left with sine squared theta plus cosine squared theta, which is just a 1. So really over here, I'm going to get negative sine phi cosine phi. Okay, so this is what I have. I have this right here, and this is my cross product. I'm interested now in doing the magnitude of this cross product. So I'll say the magnitude of r theta cross r phi is going to be, and I know I'm going to have to set up a big long square root. Each of these pieces in here has to be squared. So notice I'm going to end up with a sine to the 4th phi cosine squared theta. I'm then going to end up with plus a sine to the 4th phi sine squared theta. And finally, I'll end up with a sine squared phi cosine squared phi. So this is what I have now, and I can go ahead and think about how I might begin to try to simplify this down. Okay, well, a couple things might jump out at you right away. In these first two terms, I might notice that very easily they're going to simplify down to just a sine to the 4th of phi. Of course, then I'll be left with my sine squared of phi cosine squared of phi. But in here, I'll notice that, again, there's something that's in common. I could factor out a sine squared phi from both terms. if I was to do that, what you'll notice is that I'll definitely end up with a sine squared phi still underneath the radical. But what I'll be left with after I pull that out is going to be a sine squared phi plus cosine squared phi, which is just a 1. And over here, I'm now going to see that this is just going to be sine of phi. Now, I should note that since I'm square rooting a square, technically this is going to be the absolute value of the sine of phi. Okay? However, we should note that since our value of phi is going to be between strictly 0, or specifically between 0 and pi, I know that the sine of those angles is always positive. So then I can say that the absolute value of sine phi is actually just going to be equal to sine phi on that interval. Okay, so this is fantastic. We've been able to see that actually this cross product that took a long time to compute and looks really messy simplifies down to just this simple value. So now watch as we can go ahead and update the integral. We have pretty much all of the pieces that we need. So our double integral over sigma x squared ds, we can transform into a double integral. First, let's replace our x squared. We know that our x squared, again, with x coming from our parameterization, let's see, up here, was a sine phi cosine theta. And I'm going to square that. So this is going to be a sine squared phi cosine squared theta. Okay, so I have that. That replaces the x squared. Then I replace my ds. And remember by what we saw in the theorem up above, that gets replaced with the magnitude of my cross product, dA, which in this case would be something like a du dv or a dv du. The order's kind of up to us. So here, I can go ahead and say, now I'm going to multiply by my sine phi, and I'm just going to put down du dv. Of course, then I would need to know the bounds on u and v. Oh, wait, sorry, not du dv. Those are the wrong letters. I can do something like d theta d phi if I want, and I need to know the bounds on those, but fortunately I already have those. Remember that theta is bounded from 0 to 2 pi, and phi was bounded from 0 to pi. Now, of course, since these contain no variables, I know I'm working over a rectangular region in the theta phi plane, and so it's totally fine for me to reverse the order of this integration if I would like to. There's no issues there. Now, I'm not going to go ahead and fully evaluate this. I'm going to leave that to you, because in this video, I just want to focus on the setup. Being able to take the integral that we were given and transform it into something that's more easy to calculate is really our big goal here. Of course, I would ask that you go ahead and try to compute this integral and make sure that you get the answer that I get in the notes up in Blackboard. I'll tell you that right now, the answer you should be able to arrive at is 4 pi over 3. So give that a shot, and of course let me know if you have any questions. In the next video, we'll take a look at example number 2 and practice doing the similar sort of process again.